Yeah. So great. Good morning, all of you. So please type in the chat box. Am I audible? Yeah. So please type in the chat box, all of you. Am I audible to all of you? Good morning, all of you. Yes. Yeah. It's audible, right? Yeah. Okay. So in today's session, we will talk about pressure and its measurement, basically the hydrostatics part, and also hydrostatic forces I have split into first and second parts. First basically on plane surfaces. Okay, so we will start with this pressure and its measurement, but before going there, we will actually visit to fluid and its properties sometime. Okay, and also some topics which were left over yesterday that we are going to finish today. Okay, so जो topics कल हमने finish नहीं किया, so वो topics भी हम आज करेंगे. Now in this lecture exclusively, we will talk about this non-Newtonian fluids clearly, and we will talk about air pressure and also the techniques to measure pressure, like different devices you have, especially when you talk in syllabus point of view. We have barometers, manometers, how these devices actually came into picture, that also we will see, like the hydrostatic equation, pressure techniques and all. And then we will also discuss a bit on hydrostatic forces on plane surfaces generally. Okay, so these are the things that we are going to discuss in today's sessions. And before going here straight away, if you have the recap of the last lecture slightly, in last lecture we have started with the definition of fluid. Okay, and also we have seen certain important properties like viscosity, both dynamic and also kinematic, and kinematic viscosities. We have talked about different units and all, and then we have also seen Newton's law of viscosity. Newton's law of viscosity, like if for example if a substance is actually flowing, then the shear stress at any layer is equal to mu into the rate of shear strain. Okay, so this is called the shear strain rate, of course. Okay, so gamma dot xy, and this gamma dot xy in general is actually dou u by dou y plus dou v by dou x, where generally this u, if you take the velocity vector, let us suppose if x component of velocity is ui and y component of velocity is vj for example, then this is the expression. Then we have seen in some special cases this value gamma dot xy will be equal to, sir please bulk modulus etc बता दीजिए ना, हाँ आज पढ़ेंगे, ठीक है, so no issue. So if you see, this is dou v by dou x, and normally if you take only one dimensional flow, and that too in one dimensional flow, if this u is depending only on function of y, then this expression becomes equal to dou u by or du by dy actually here. Okay, so this is a du by dy. We have seen these things. Okay, and this is the general Newton's law of viscosity. Now coming to liquids, in case of liquids, we have seen as temperature increases, dynamic viscosity of liquids actually decreases. Okay, and the main phenomena here is molecular cohesion. Molecular cohesion. And we have seen in case of gases, like as T increases, the dynamic viscosity of gases will again increase. Okay, and here the viscosity mechanism is basically molecular momentum transfer. Molecular momentum transfer is what the main mechanism responsible for viscosity. And you have also seen kinematic viscosity of gases is actually proportional to T absolute power 3 by 2. We have seen this equation. And also dynamic viscosity of gases is approximately proportional to square root of T absolute, and of course this relation is actually exponential. Exponential, correct? So we have seen these things. So we have seen how with respect to density how things change and all. And now in basically again from here I have told you one thing, that if you take any curve, for example if you take two fluids like this, let us suppose if this is tau and this is du by dy, because you can see this generally if these two are Newtonian fluids, then definitely this fluid has mu1 dynamic viscosity, and if this is mu2, definitely mu1 is greater than mu2 obviously. Okay, and yesterday I just left one particular point. Can anyone tell me what is the relation between these two, kinematic viscosity of air and kinematic viscosity of water? Can anyone tell me what is the symbol that fits less than, greater than, equal to something? Can anyone tell me what is the symbol here? Greater than or less than or equal to something? Less. or more? Come on. It is actually greater. Okay, because see, dynamic viscosity of air is definitely less as compared to dynamic viscosity of water. We all know this. Okay, because in a layer, normally if you move your hand in water and if you move in your hand in air, definitely you can move your hand easily in air because air offers you less dynamic viscosity. But लेकिन अगर आपने kinetic viscosity की बात किया तो if you divide this with the density of air and density of water, this density of water is almost like thousands of times higher, correct? Like generally of air, like for example at air, if you have 1.2, 1.4, even in case of compressed air is 1.6 maximum, that's level that we go. But in case of water, density of water is around 1000. Okay, so compared to these two terms, definitely density of water is very high. That's why the kinematic viscosity of water is actually very sorry, here I cannot do the division directly. Just to explain you, I am dividing, but actually you can see when you divide with densities of water, this term will decrease drastically and obviously this term will be small. Okay, so density kinematic viscosity of air is actually large in that case. Got it? Because this is one very important question that again people ask you when you go. They'll ask you kinematic viscosity of air is more than water or less than water. Then you have to ask them which viscosity, sir, it's dynamic or kinematic. If it's dynamic, then definitely water has higher dynamic viscosity. If you talk about kinematic viscosity, definitely air has higher kinematic viscosity. Got it? Is this 2 points clear to all of you? Okay. Now, so these are the things after that we have discussed in yesterday's class. And also before going for next topic, let us solve this question because this is homework what I have given you in yesterday. Okay, the other question was very dead easy. Okay, so this question is somewhat slightly mathematical, so that's why we will solve this question. The other question is very simple. You can see whenever you have two layers of fluid, for example, if these are the velocity profiles, then definitely if this is the interface, if this interface is moving at uniform velocity, then can anyone tell me what should be the net force acting on this layer? If this layer of fluid is moving at uniform velocity, that means can I say what is the net force acting on this layer? So first में force नहीं है, area कैसे निकले? Per unit area, that's it. Okay, fine. So can anyone tell me what is the net force acting on this layer? Obviously, if the fluid is moving at uniform velocity, if the layer is moving at uniform velocity, that means net force acting on the fluid is obviously 0, correct? So this net force acting on the fluid is 0. That means you can clearly see if there is a fluid layer like this, then shear stress acting and on the top should be same as shear stress acting on the bottom actually. Okay, because area is same for the fluid layer on top and bottom, so these two we have to equal. So obviously mu of the top fluid into velocity gradient in the top fluid should be say at y is equal to this particular value. I think this center coordinate is what I have taken. So at y is equal to 0 is same as mu bottom into du by dy at y is equal to 0 for the bottom layer. That's it. If you do, then you can get the relation between dynamic viscosities and also forces obviously. Okay, so that's a very simple question, but coming to this question, it's a slightly nice question, so we will see that. Okay, and this question what I have deleted basically that's available in a lot of books actually, Parakram, 𝐂𝐤𝐬𝐿. Okay, in all these books you have that question. Okay, now coming to this question, see carefully. This is a cylinder. Now clearly if this cylinder is moving, that means it moves because of two forces. I mean it moves in the vertical direction because of this weight, but again it slow down because of this viscous effects. Okay, so this is a thin oil film of H. Okay, so if you draw the free body diagram, you have weight which actually moves in this direction, which actually acts in this direction, and also since this is a cylinder, all over the 360 degrees of this cylinder there is viscous effects. Yes or no? Because this cylinder is actually moving in a sleeve. So if this cylinder is actually moving in a sleeve, then this cylinder is surrounded by viscous fluid by all 360 degrees. Okay, so that means the viscous force keeps acting at all these locations basically. Okay, at all the 360 degrees. Okay, now you can see definitely these are the only two forces which are responsible for motion. Weight minus viscous force is equal to mass. Mass can be written as weight by gravity into acceleration. Okay, so weight by gravity into acceleration. Now weight is anyhow mg or w if you leave that. What about the viscous force actually? Viscous force is nothing but total shear stress, shear stress into total area. So shear stress tau into area. Can anyone tell me, if this cylinder is 360 degrees rotated by fluid, is surrounded by fluid, then what is the area of solid fluid contact? Come on, if this cylinder is completely fitted in a viscous channel, then can anyone tell me what is actually the okay, fine, I told the answer then. So this is mu into, let us suppose if this is moving at a velocity v, then within this small thickness h, oil velocity at any point on this solid fixed is 0, at any point on the cylinder is v in this direction. So within a gap of h, the velocity is increasing by v. So this is the velocity gradient. So mu into velocity gradient gives you shear stress multiplied with pi dl is what you have here, correct? So pi dl, obviously, yes, good, all of you, fantastic, pi dl. So this is w by g into acceleration dv by dt. Okay, actually should write vectors, but anyway, you know, motion is only in the y direction, so I'm writing only this. Now you can clearly see w minus pi mu dl by h into v is equal to w by g into dv by dt, obviously here. Okay, now you can clearly see if you multiply g by w all over, this is g. Okay, or else you can fine, anything you can do. Let us suppose, yeah, better you can divide this. So g, if you divide this, we have a g here and we also have a g here. Okay, and w, if you divide, this w gets eliminated and you have a w here. Okay, that's it. So this implies the equation is g minus pi mu g dl by wh times v is equal to dv by dt, obviously. Now this term in the bracket is a constant, yes or no? Because pi is a constant, obviously. Mu, we are taking no variations with respect to any temperature and all, because nothing, no heat is getting interacted. G is obviously constant. Diameter and length of the cylinder are fixed. Weight of the cylinder is fixed, and this oil film thickness h is also fixed. Understood? Yes or no? Because you can see just in this equation, this viscous force I have written is equal to weight by g into acceleration I have written as dv by dt. Then this is just algebra simplification, and this gives you this. And since you can understand one thing, this term which is here in the brackets, this is actually a constant k. Okay, so this is a constant k, obviously. Now this is a single variable differential equation, obviously. So if you solve this, let us see what you have. G minus constant times v is equal to dv by dt. So this can be written as 1 by g minus kv dv is equal to dt, obviously. Okay, so this is what you get. Now you can see, if you take this integration, initially at time t is equal to 0, what is the velocity? Let us see. Is covered by viscous oil of film thickness h, then the expression for the velocity of the cylinder as a function of time slides down from west. Okay, so slides down from west means at time t is equal to 0, what is the velocity actually here? Can anyone tell me at time t equal to 0, what is the velocity? It is starting from west, is given in the question. So obviously, what's the velocity at time t equal to 0? Because writing boundary conditions when you solve a differential equation is very important, even in heat transfer or in fluid mechanics, or basically in strength of materials when you are doing beams and all. Writing boundary conditions is the most important thing. Okay, so v is equal to 0. So at time t, let us suppose if the velocity is v, so this is a single variable, variable separable. We all like variable separable forms. Okay, so this integration is minus 1 by k times ln g minus kv within the limits 0 to v is equal to time t, obviously. Okay, now this implies, basically if you can see, log, when you put v is equal to v, this is ln g minus kv, minus when you put 0, this is v is equal to 0, this is ln g. So log a minus log b can be written as log a by b is equal to minus k. Okay, and if you simplify this, obviously this is 1 minus kv, so kv or 1 minus e power minus kt is equal to kv, obviously. So v is equal to 1 by k times of 1 minus e power minus kt. So what is k? This is the expression, and clearly you can see this is an exponential. Okay, means whenever any body starts traveling in a viscous channel, then definitely if you leave that particular body, the body travels with a constant basically some deceleration. Initially it accelerates for some time and then it decelerates, means the slope will be positive for some time and then the slope turns out to be negative, and this body will actually reach a particular a particular velocity which is called the terminal velocity. Okay, and this is the graph of that. You can clearly see if you plot this. For example, if you take k is equal to 2 and if we plot, I'll show you the graph also. See here, Desmos, yeah, better. You can see for example, k is equal to 2, okay, you take k is equal to 2, let us suppose this constant value is equal to 2 or 3, anything. So 0.5 into 1 minus e power minus 0.5 t, okay, or else simply I'll show you this thing. If you take k is equal to 1, the things will be easy. 1 minus, 1 minus exponential of minus x actually, okay. So 1 minus exponential of minus x, you can see the graph is something like this, okay. So you can see, if you zoom in, then you can clearly see, okay, this much zoom in is fine, I think. So let us suppose at time t equal, let us ignore the negative part of the time, okay. So if you take only positive part significantly, the velocity keeps increasing, and there comes some situation within 3-4 seconds, the body attains certain terminal velocity, okay, and this depends on the constant k, obviously. Got it? Okay, so that's how you all can see this graph, okay. So starting from 0, then this graph, the velocity, if this is velocity and if this is time, then the velocity keeps increasing, and there comes a particular saturation at some particular location of time, okay. And what is k? From our assumption, we have taken k is equal to, with this constant we have fixed as k. So 1 by k is WH by pi mu g dl into 1 minus e power minus k again. So k is WH, k is actually pi mu g dl by WH into time. That's it, okay. So this is how we have the equation if you substitute. Anyway, if you take this term constant, you can see this h is actually written in the denominator. That's it, okay. So this h is actually written in the denominator, so you can see one of these equations will actually fit the thing, okay. Can we find at what time can we get terminal velocity, sir? Yeah, definitely. Like for example, generally if you this depends on this constants. If you plot this equation, okay, if you can plot this equation, you will, like for example, if you exactly know the value of k, because if I give you all the properties like mu, diameter, length, weight, if I give you all this, then definitely you can get this constant k. So here you can actually plot the equation very correctly. Like for example, let us suppose if all the quantities give you 2, okay, then 2 multiplied with 2 multiplied with then obviously when I multiply minus 2x also here, okay, it comes out to be minus 2x, okay. Then you can see the curvature of the graph got changed, and almost roughly at 2.8 seconds somewhere it is touching this, it's becoming very asymptotic to this particular value, okay. And you can see the steady state velocity is roughly 1.996, it will touch 2 obviously, okay, because you can see whenever if you put t is equal to infinity, for example, okay, after some sufficiently long time, when t is equal to infinity, or basically after certain sufficiently long time, this exponential term will become 0, yes or no? So v terminal will be 1 by k, that's it. Understood? So all these things can be understood geometrically from graphs and also from solving of analytical things. Clear? Is this question clear to all of you? Because it's a nice question. Because many of you may feel one thing, that if you leave a body, its velocity generally, let us suppose in atmosphere if I leave a body, then what happens? It continuously accelerates, okay. But in case of viscous effects, that won't be the case, okay. So initially the body keeps accelerating, but the acceleration keeps decreasing as time increases, and obviously it attains some steady state velocity after some time, okay. Now fine, so let's continue our discussion basically on topics. Non-Newtonian fluids is there, and before non-Newtonian fluids we'll also talk about certain important things like Bernoulli's, all that I have confused. So can we, is this clear now? Is this clear to all of you? So please type in the chat box. Is this clear to each and every one of you? The question what we have discussed here till this point. Okay, fine. Now let us see, before going to non-Newtonian fluids, I would like to give you one important thing actually here. So if you see, like for example, first initially we'll talk about bulk modulus for a while, and also we'll talk about surface tension, then we will look at non-Newtonian fluids, okay. So because they are a bit of importance. Now you can see this bulk modulus, for example, if I denote this with E, any modulus, okay. So normally this bulk modulus we denote with E, elasticity modulus in general in fluids. Now you can see this E is the measure of compressibility in one aspect. Like for example, this is given by dP by dV by V with a minus sign, obviously, okay. So why this minus sign actually comes out, okay. Let us suppose if we take a body, for example, let us suppose initially there is atmosphere acting on the body, for example. Okay, now if you can understand, let us suppose if I increase pressure on this body, let us suppose initially it is atmosphere at every location. This is atmosphere. Now let us suppose if I increase the atmosphere pressure, if I increase the pressure from P1 to P2, let us suppose on the body, if I am changing the pressure from P1 to P2. Okay, so this is P2 and here it is P1 actually. Okay, so this is P1. Now can anyone tell me, if I am increasing pressure, my dp is always final minus initial, so dp is positive or negative? If I am increasing the pressure, then dp is positive or negative? Can anyone tell me? If I increase dp, for example, then dp is positive or negative? It is positive, right? Because P2 minus P1 will be positive, obviously. Now whenever I increase the pressure on the body, what happens to the volume? Obviously, what happens to this dV? Look, P2 is greater than P1 clearly, so this implies dP is positive. Now if you generally increase the pressure on the body, the volume will actually decrease, right? So for a positive increase in pressure, this dV will be negative. Okay, so if I increase the pressure on the body, this dV will be negative. So that's why these two are contradicting in nature. If this is positive, then definitely this has to be negative, or if this is negative, this has to be positive. So to compensate for the modulus, we put a minus sign here. Got it? Okay, that's how we have the minus sign. Like this you can see in many times, like heat transfer in conduction is proportional to minus of gradient of temperature. Okay, temperature is a scalar, so you can take a gradient for that. So this is good. Again you put a minus sign because gradient of temperature will be negative, generally in the direction of the heat flow. If you see the temperature gradient, that will be negative, obviously. So to see this magnitude, we put a minus sign. We'll see a lot of things like this. Then whenever you have this, mass of substance is always constant. Yes or no? Means whatever I do to this body, this mass which is remaining here is always a constant. Yes or no? Because mass of the body cannot change. We cannot create mass, we cannot destroy mass and all. So this is what we have. So density into volume, for example, if I denote this with a cut, so density into volume is equal to constant. Now if you differentiate both sides, first function into derivative of second function plus second function into derivative of first function is equal to derivative of constant, which is 0. You can see dV by V can be replaced with minus d rho by rho, obviously. Okay, if you replace this here, the same expression for bulk modulus will actually give you is equal to E is equal to minus dP by dV by V, which is also same as dP by d rho by rho actually here. Okay, so this is what we have. Now the main thing here is, obviously here minus sign won't be there because this mathematically eliminates the minus sign. And second important point, bulk modulus is used as a measure to identify the compressibility, and also one particular term which is called compressibility. Compressibility normally denoted with K. So this K is actually equal to 1 by bulk modulus, and this, as the name implies, this also is a measure of compressibleness of a system generally here. Okay, so this is also a measure of compressibleness of a system. But normally when you are compressing any substance, two things happen. One is the temperature of the system increases. Normally you might have seen this whenever you are filling your cycle tube, for example. Okay, when you are pumping the air, after some time when your leg touches the cylinder, then definitely you will feel some hotness in the cylinder. Okay, because whenever you compress anything, because of the intermolecular forces, they start certain friction, and obviously the temperature of the system increases. So when you are compressing, you should decide whether to make the compression adiabatic or to make the compression isothermal. And obviously, you know, from your basic thermodynamic knowledge, if you apply TdS is equal to dH minus VdP, you can clearly identify adiabatic compressions are obviously the possible compressions, but the best is isothermal compressions. Okay, so right now we are not doing, because I think Shivam sir might have already taken you to that in properties of substances. Now you can see This bulk compressibility is what generally we take as adiabatic compressibility, because adiabatic is generally easy. And in our fluid mechanics, in this particular course, we don't interact with any heat interactions into the fluid. Yes or no? Like for example, later in flow through pipes or at any location, we don't deal with heat interactions. Okay, normally we'll have only 4 equations and 4 unknowns. We'll solve for them. We will see what are the 4 equations and 4 unknowns, but this is what you have. This is the adiabatic compressibility. Okay, now if you see for water, this is around like 2 into 10 power 9 kilonewton per meter square. Okay, almost like 2.01 in that range. So this is the bulk modulus of water in general. Okay, and air is actually 20,000 times more compressible than water on an average if you see the magnitude. And one important thing here is, you can see this K. Obviously this K, how this is a measure is because, let us suppose if a substance has high bulk modulus, for example. Okay, let us suppose if a substance has high bulk modulus. If a substance has high bulk modulus, that means, what is the meaning? To create 1 unit volumetric strain, the dP that I have to apply is actually high. Yes or no? That's what it means, correct? If my this bulk modulus is high, that means for creating a unit volumetric strain, but let us suppose if the denominator is 1, for creating 1 unit volumetric strain, this dP has to be very high, correct? So if dP has to be very high, that means it is difficult for me, means to compress a substance or basically to create some volume change, the pressure change what I have to apply will be very large. Okay, so if E is very large, then K is obviously very small, because this K denotes compressibility in general, and compressibility of the substance is actually small. That's how all these things are connected to each other. Clear? Okay. So is this clear to all of you? Please type in the chat box. Yes. Now let us continue. And obviously for air, if you see, normally at atmospheric conditions and all, it is like 101 kilonewton per meter square roughly. Okay, so these are the things that we have, kilonewton per meter square, and this is 2 into 10 power 9 kilonewton per meter square roughly. Now if you try to understand one thing, I would like to emphasize on 2 important things. Crystal clear? Got it? Yeah. So yesterday class PDF will not be found out. Harsh, I think app पे है. Okay, so जो links है description में, वो links पे जाइए तो आपको PDF मिलेगा पक्का. Okay. Now let us see one very important concept, and also interviews के लिए बहुत भी important है. Incompressible fluid and incompressible flow. Incompressible flow, obviously. So these are 2 important terms, and many times people get confused between these 2. Okay, they say one for another. Now so please explain viscous force once in problem. Yeah, I'll explain you. Okay, just let us finish this. See here, this is incompressible fluid. Just now we have seen, to identify whether fluid is incompressible or not, we focus on bulk modulus. Bulk modulus. Okay, so this is bulk modulus. You know, generally we declare if E is high, then obviously the substance is incompressible. Very high. Let us say very, this word is important sometimes, is incompressible actually. Okay, incompressible. Now sometimes what can happen is, even this incompressible fluids, let us suppose if for example I have some water, okay, I have taken some mass of water. Practically everyone know the bulk modulus of water is very high, so definitely it is very difficult to compress water, so generally we treat water as incompressible substance. But if the pressure on the water is sufficiently enough to create some volume changes, obviously for the same given amount of mass, if volume is changing, density will change, obviously, because mass has to be constant. So let us suppose if I take some volume of water, if the pressure applied on the water is sufficient to create volume changes or basically density changes, then definitely this incompressible fluid, or basically very highly bulk modulus fluid, is undergoing some compression. Yes or no? Means the fluid which we are supposed to be incompressible because of high bulk modulus, but in some applications due to high application of pressure, this incompressible fluid or the fluid with a high bulk modulus will actually experience certain compressibility effects. Yes or no? Now let us suppose, if for example, if you have a fluid flow, let us suppose a fluid is flowing, for example. Now normally when a fluid is flowing, generally there happens certain pressure loss between two sections because of various reasons, viscosity, friction, all this stuff. Okay. Now let us suppose if the pressure difference between these two sections, let us suppose some type of flow is happening, and the pressure difference at these two sections, 1, 2, P1 minus P2. Let us suppose if this pressure difference is very large, such that this pressure is able to compress or create density changes in this region. Let us suppose in this flow, let us suppose if the pressure difference P1 and P2 is good enough to create certain density variations in this region, because obviously the fluid will experience certain compressibility effects because of this high pressure difference. Okay, so in such cases we cannot say the fluid is incompressible, but the flow is actually not incompressible. Clear? Because if somewhere in this flow the substance is actually experiencing density variations. Understood? And that's why if you see, if this is P1 minus P2, generally to identify its incompressible flow, if you normally later will see order of the change in pressure in a flow will be of the order rho v square by 2 in general. Okay, which of course since you have already studied fluid mechanics, in Bernoulli's equation you will write P by rho g plus v square by 2g terms like this. Okay, so in general the change in pressure magnitude will be of the scale of kinetic energy. If you compare, many times you will even neglect the potential heads, because the contribution due to the pressure and velocity heads is very major in general flows, and this is the case. And normally if you do bit of analysis, which I'm not doing right now, it's actually derivable part, maybe in some detailed course of YouTube and all, I'll take some time later. But right now you can see we end up with something called this, where V is velocity of the flow or actual velocity of the flow, actual velocity of the flow, actual velocity of the flow, and A is called acoustic velocity. Acoustic velocity in fluids. Okay, I think Shivam Samet have definitely taught you this in thermodynamic relations, that acoustic velocity is equal to root gamma RT, or this is also given by 1 by K times isentropic compressibility into density. So we have certain expressions like this. Okay, so using all this bit of thermodynamic, we can get Mach number. This is actually called the Mach number, dimensionless number. So this is Mach number, and this is called V by A obviously here. Okay, now this is actually V by A. This acoustic velocity has to be taken only at this particular situation of the fluid. Okay, let us suppose because of being compressed, the compressibility of this substance got a new value. You should calculate the acoustic velocity in that medium, and if this ratio is less than 1 by 3 generally, or 0.33 sometimes we write. So if Mach number is less than 0.318 is the actual value, so 32, but sometimes for calculation benefit we take 33 actually. Okay, because actually we will get Mach number is equal to half times of d rho by rho and all. When this density variations is less than 5% and all, we will do certain analysis. Okay, so right now if you see this Mach number is less than 0.32, the flow is incompressible. Incompressible. How we actually get this constant is, look, if you apply this Bernoulli's equation and if you connect this delta P using bulk modulus, you will end up with certain equation. Obviously, you have also seen Mach or acoustic velocity. One more expression for acoustic velocity is isentropic bulk modulus by density. You might have seen this. A is equal to square root of E by O in thermodynamics. So when you convert this pressure using bulk modulus, and if you convert, we experience that if the density variations in this regime is less than 5%, means if dO by O is less than 5%, we treat practically the flow as incompressible, and the Mach number value corresponding to this value of 5% is 0.318 or 0.32 generally. Okay, so this is how we actually decide whether a flow is incompressible or not. Okay, even incompressible or fluids with very high bulk modulus can experience compressibility effects in the influence of high pressures actually. Okay, so that's why you can see, to decide whether a fluid is incompressible or not, we actually go for bulk modulus checking. Okay, if bulk modulus is very high, fluid is incompressible. Then if you want to observe whether a flow is incompressible or not, you should check the Mach number of the flow. Clear? This is only for perfect gas. Obviously this is only for perfect gas. These are the two general expressions obviously. Okay, this root gamma RT is only for perfect gas, because if you do bit of thermodynamics, this 1 by Ks into rho, all this adiabatic compressibility minus 1 by V into dou V by dou T at constant adiabatics, all these things if you do, you will actually get these things. Okay, is this clear to all of you? Did you all understand how to identify the difference between a compressible flow and incompressible flow and an incompressible fluid? Clear? Crystal clear to all of you? Because that's really important sometimes. Okay, people generally don't know, they assume this O is constant everywhere and say incompressible fluid, incompressible flow. People shuffle between this, but actually you should have clarity. Okay, for checking fluid you should look at bulk modulus, for checking the flow you should look at Mach number. Okay, now let us see. So this is the bit of story about the this bulk modulus. Now one last property I would like to talk about is surface tension. Many times this is actually important. This is slightly important because this is actually a binary property. Like for example, you take density, dynamic viscosity, kinematic viscosity. These are individual properties of the fluid itself, but surface tension will actually depend upon the fluid, and also basically thermal expansivity will seen better in thermodynamics, or else thermal expansivity, if you see, this is 1 by V dou V by dou T at depending on adiabatic conditions, or at whatever you have the isothermal expansivity or adiabatic expansivity, like compressibility you have similarly. This is the expression for different substances. You can calculate this value. In some books you denote it with beta also, volumetric expansivity. Okay, like in case of ideal gas, this value comes out to be 1 by T. Fine. So we will see accordingly. Okay, now let us see here, if this is binary property, what is this binary property is. I'll give you some 5 to 10 minutes of understanding, good understanding on surface tension. Look, let us suppose if I have a fluid surface, for example, then if you take any molecule deep inside, this molecule is attracted by all other surrounding molecules, correct? Because in liquids the molecules are still close to each other, so we actually have a balance. And this sphere which is here is called sphere of influence. Sphere of influence, actually. Sphere of influence. Similarly, if you take another molecule here, same thing happens. Obviously, it again is exerted force on this molecule by all the other surrounding molecules. Okay. Now, in such situations, so Mach number for sound and fluids are based on different or same concepts. Same concepts. Okay, the expressions change depending upon gases and fluids, but this definitions of isentropic adiabatic bulk modulus by density, or root of 1 by density into adiabatic compressibility, these definitions remain same for any substance, even for solids. Okay, like for example, you take solids like steel and all. Whenever you subject them to very high pressures, then definitely they actually change. Okay. Now, anyway, coming to here, you can see, if this is the sphere, can anyone tell me what is the net force acting on this molecule because of all these surrounding molecules? Can anyone tell me what is the net force acting on this particular molecule by all other molecules? It's easy, right? So please guess, what is the net force acting on this particular molecule due to all the other molecules? It is 0, right? Because obviously this gets balanced by this gets balanced by this, and similarly here. But I'll ask you one thing. Let us suppose if we take a molecule on the surface or very close to surface, then what happens here is the story is slightly different. It gets attracted by all these molecules as usual, but on the top, whenever there is an interface, let us suppose if this is interface, you have maybe two fluids, generally, one can be liquid, one can be gas and all. So let us suppose, for example, in this instant I am taking gas here. Okay, for example, I am taking gas in general, gas. Now we have two forces, cohesive and also adhesive. Okay, this cohesive forces is between similar molecules, like let us suppose all water molecules, they exert cohesion, and this is between dissimilar molecules. Dissimilar molecules actually. Okay. Now, whenever you take a particle at this location, whenever you take a particle at this interface, all these downward forces are acting at the same time. Definitely the particle which is here is also exerted to some adhesive forces, yes or no, because there will also be forces due to the other interface or the other substance which is at the interface. Now if you see clearly, let us suppose if you take gas for example, and if the compared to gases, liquids have stronger cohesions, so you can see there is a pulling in this, and also there is also a pulling on this, but clearly the net force on the molecule is not balanced now, yes or no? Clearly you can see, because downward there is a high cohesion, and on the top at the interface due to the other fluid, the cohesion or the adhesion forces are slightly weak in this case, yes or no? Which means the molecules on the surface are actually subjected to certain imbalance between cohesion and adhesion, yes or no? Can you feel this? Can you feel this? So please type in the chat box. Can you all see clearly that this molecule which is at this particular interface is not balanced in terms of mechanical equilibrium? Correct? Can you all accept this? Everyone should type in the chat box. Okay. Now the main important thing here is, let us suppose if this fluid I am keeping it as water. Let us suppose I am changing this fluid. Okay. In one case I have kept air, in one case I have kept oxygen, in one case I have kept helium. If I keep on changing this gas, the magnitude of the top part of the forces will change, correct? And between, if you change any of these fluids, then definitely this imbalance will not stay constant, it will change definitely. Okay, let us suppose if this gas is changing, then definitely this upper half of the forces will change, and definitely the imbalance, let us suppose initially if it is water and oxygen, if this is some 40 newtons for example, then if you change this oxygen to helium, then definitely this 40 will change. Okay, so there exists the surface is at some imbalance between cohesion and adhesion. Now if you take any small particular, if you take this particular part of the surface, you can understand whenever this is a surface, clearly there is a net effective force in this direction and also a net effective force in this direction. Now let us suppose you take a small rubber strip for example, and if you apply forces in the downward direction, what happens here? This surface will actually stretch, yes or no? There happens some stretching, localized stretching happens. Localized stretching happens, correct? So in that small particular fluid layer, this layer will be subjected to certain stretching because of this forces. Clearly you can see here, if you see for this half you take the resultant like this half you take the resultant like this, it happens. Okay, now if this surface is stretching, what is the nature of the force inside the surface? Tension or compression? Can anyone tell me? If this surface is subjected to stretching like this, then what is the nature of the force inside the material? Come on. It is tension, obviously, correct? It is tension. So if that's tension, obviously because of this imbalance, since the surface is experiencing certain stretching or certain tension forces, that's why it's simply called surface tension, because the surface is at some tension. That's it. Okay. If you are pulling this rubber sheet for example, then definitely if you are stretching inside at every location, there is a tension force, right? So therefore it is basically surface tension. And if you want to define the magnitude of the surface tension, this is due to imbalance, but if you want to quantify it, okay, in some mathematical term, you can, normally this is denoted with sigma, and you should always write these conditions, okay, between which two fluids is this value you are writing, okay, because it's not like it's not sufficient if I write the surface tension of water is, no, that statement is wrong. The surface tension at the water air interface is dash. That's how we have to write. Okay, fine. Sorry, there are some comments. Super 1500 में normal हिंदी में पढ़ा है हो, so वैसे ही पढ़ा हो, इसे बहुत कम समझ आता है, please sir. Okay, Parmish, I'll try to go it in Hinglish. Okay, so अगर एक ही कंटेनर में दो लिक्विड लेंगे तो दोनों लिक्विड के इंटरफेस पर सरफेस टेंशन फिनोमेना होगा पक्का. Okay, if this is under surface tension, let us suppose if this, normally we say the interface is under tension. Okay, it's not like interface we cannot clarify into two, like how you define definition of boundary in thermodynamics. Boundary do not belong to system and also surroundings. Similarly, whenever you're talking about interface, we don't say that interface is either in gas or in liquid, but it's an interface again, it's an imaginary. Okay, so therefore at that level of interface, definitely every molecule is locally subjected to stretching. Okay, and that's how this happens. Now if this is sigma, sigma is actually denoted by force per unit length. Now what is this unit length? Look, now let us suppose if I take a line of molecules which is perpendicular to this surface. Let us suppose if this is the surface, if I am seeing from the top view, let us suppose if I take a line which is like this, perpendicular to this, then what I'll have, in the top view I'll see a line like this. On each line you can see clearly there are molecules, correct? This line is actually top view of this surface. Okay, when I'm taking a line of length which is perpendicular to this board, then this is how you can see. So let us suppose if this line length is L, then definitely at every point it is subjected to some stretching, localized stretching, and this intensity, linear intensity, means intensity per length, is nothing but surface tension force actually. Okay, so this is your surface tension force. This is sigma. Obviously sigma is F by L, where L is this length of molecules. Clear? Okay, generally of oxygen, because oxygen has higher molecular mass comparatively. Okay, clear? So this is how we have sigma is equal to F by L, obviously. Okay, and this L is actually this perpendicular length of the molecules. Clear? And if you talk about the dimensions, clearly SI is Newton per meter. You can convert to MKS and all accordingly. MKS, for example, Newton can be written as kg meter per second square into meter. Okay, that's what you have. So definitely you can see this meter gets cancelled. Kg second square power minus 2. So in grams, gram second power minus 2, obviously. And so dimensions of sigma is like m kg per second square. So m t power minus 2. That's it. Okay, all clear? So सबको समझ में आया surface tension कैसे पढ़ना है? Okay, is this clear to all of you? Now let us see one more thing. If you have a fluid body, for example, if you have this fluid body, there are certain consequences of this fluid bodies. Consequences of surface tension. Look, I want to tell you one thing. If you have a fluid body like this, now if you take different molecules on this surface, for example, first of all I'll explain you geometrically, then I'll tell you mathematically also. So see, if you take these fluid particles, for example, let us suppose if this is subjected to stretching like this, similarly this is also subjected to stretching. That means at every point on the surface of the body, this particular interface, you can see this tries to get localized curving, yes or no? So it tends to get localized curvature at every point. So this stretching will happen at every location locally, and finally we will see that this surface area, because it's stretching at every direction. So let us suppose if this is the molecule, they are all trying to form a group together, like how players assemble in front of just before the starting of a match, how players assemble. Similarly, like that, all these are trying to assemble in a close way. So because of the cohesion forces, cohesion is strong, so obviously these molecules, all these molecules will also be tried to pull towards the center, and also they are also locally pulling each other. So can anyone tell me, if this pulling locally happens and if all the molecules are taking a local curvature because of the stretching, what could be the shape at the equilibrium of this particular fluid? Can anyone tell me what could be the shape here? It is cohesion, yeah, cohesion, molecular cohesion forces. Okay, because it's a chunk of fluid, obviously. So can anyone tell me, if all these are assembling close and also in all the 3 dimensions, the fluid particles are coming close to each other? Okay, it is circular, correct? So it is circular in 3-dimensional because fluid is generally, here the diagram is 2D, so you are telling circle. If I take a 3D in general, then definitely what could be the shape of this object? because of the localized stretching. In 3D, what happens? It is spherical. Okay, so obviously, therefore, first consequence is in general, raindrops are spherical. Okay. Second, normally, clean washing of clothes with clean washing with hot water, or detergents also, if you add detergents. Have you ever seen in your home, jab maa kapde, when she cleans the clothes, whenever if you want to clean the clothes with very high, dirt or something, you use hot water generally. Normally, if you want to wash clothes, you generally wash with cool water and you take out. But in general, if you want to wash some clothes with very high dirt or very long time, you will use hot water, correct? And also, generally you put detergents. The consequences why you are putting detergent or why you are using hot water is basically due to surface tension. The reason is, see, I'll tell you. Let us suppose you have a fabric like this, okay? If you zoom in your clothing under a microscope, this is what you will see normally, fibers, okay? In general, what happens is some mud particles will go and sit inside. Okay, so these are the mud particles. These are the mud particles actually. In normal times, what happens? When you soak this cloth in water, let us suppose if water molecules are coming here, for example, because of the strong cohesion between water molecules, and because of less adhesion between the cloth and this solid cloth and this water particles, this water particles will not be able to enter into the narrow gaps between the fibers. Okay, did you understand? Means basically, this fluid molecule here, or this fluid mass here, is actually subjected to adhesion because of this cloth, and also due to cohesion because of the surrounding fluid. Now obviously cohesion in water is generally strong, so because of hydrogen bonding and all, so clearly this water cannot actually get into touch with the cloth actually. Now what's happening? Whenever you are putting hot water, as I told you in yesterday's class, whenever you have two liquid molecules connected with a bond, if you supply heat energy to this, these bonds get weakened and these molecules will be capable of vibrating or moving far away in their random directions. Yes or no? So that's how when you do hot water, when you use hot water, first of all, because of this bond interruptions, because of hot water, definitely when fluid goes or basically whenever this cloth is subjected to certain fluid, the fluid molecules will feel more easiness in going into the deeper pores. Okay, and how detergent is helpful is, detergent is actually a pollutant of water. Normally in case of detergents, what happens is, have you ever seen, let us suppose if I ask this simple question, detergents, let us suppose if I give you some detergent with very high size of grains and some detergent with very like fine powder, which detergent you want to take generally? Anyone? It's a common experience. Even if you go to your mother and say, if you show two detergent samples, one with very high ball size, okay, let us suppose if detergent is in some small balls of size, okay, which you generally find crystals, grains you call. So let us suppose if one detergent is having high grains and if one detergent is like very smooth powder, then if you go to your mom and if we ask you which you want, obviously what she'll choose? Any idea? Market mein bahut hai na, Tide, Wheel, Nema, all these things. Obviously fine she'll choose, correct? Why fine particles has to be chosen? Because pollutant means it disturbs the cohesion. Okay, so if you see, whenever there are water molecules like this, what happens is generally, if you move inside, if this detergent particles enter inside, let us suppose if this is water molecule and if this is water molecule, if these two are exerting cohesion, now let us suppose in middle there came one detergent molecule and it sat inside, then definitely what happens? This cohesion between these two molecules gets disturbed. Yes or no? Because intermediately some other substance has come into the picture. So because since some intermediate thing has come into the picture, then definitely these two particles cohesion or the cohesion between these two particles gets affected, and if those two particles cohesion is getting affected, the water molecules feels easiness in penetrating into this pores, and obviously when water and mud get into contact with each other, water will actually take out the mud easily. Okay, so that's how surface tension is actually helpful, and these are the logics behind why you actually use these things. Okay, clear? Is this clear to all of you? Did you all understand the physics behind this. Okay, now coming to this mathematical explanation, look, I'll tell you, there is some important concept called surface energy. Surface energy. So what is this particular surface energy? See here. Let us suppose this is a free liquid surface. Let us suppose you have a fluid molecule here, for example. Okay, then this fluid molecule, sorry, anything? Yeah, missile formation basically, yeah, great. Okay, so all fine. So now if you see, let us suppose you have a molecule here. This molecule is actually mechanically at equilibrium, yes or no? Because the sphere of influence is actually good. Now, if you have this sphere of influence balanced, if I want to move this molecule to this, means if I want to create a surface, actually, how do you create surfaces? You can easily understand. Let us suppose you take a, many of you might have played since childhood also. Okay, let us suppose you wash your hand with soap, and if you blow air, then definitely some bubble starts forming, yes or no? Let us suppose if you take some soap solution and if you blow air, then definitely what happens? This bubble starts forming. If bubble is getting formed, bubble is obviously made of fluid elements, water plus soap solution. So when this bubble is getting formed, that means some surface is actually getting generated, yes or no? Previously that surface of the soap solution was not there, but now because of the blowing of air, some soap solution is actually forming a bubble, which means some surface is getting created. So like that, surfaces are actually created. Okay, now to create a surface, what you practically do, the particle which is somewhere deep inside the fluid, you are bringing it to the surface. Like for example, you can see this, you may understand bit easily. Let us suppose you have a small piston here, for example, and here there is a soap film, for example. Okay, so this is actually a soap film. Okay, this is a soap film. If you pull this plate with a force F slowly, then what happens? This film gets extended. Initially, the particles which are inside the fluid, now they actually come to the surface for creation of the surface. Correct? Because already जो पार्टिकल्स ऑलरेडी सरफेस में है वो सरफेस में ही है, लेकिन नया सरफेस फॉर्म करने के लिए जो पार्टिकल्स अंदर से आते हैं ना, सो वो पार्टिकल्स हमने सरफेस तक लाने के लिए कुछ काम करना पड़ेगा. क्लियर? एंड दैट वर्क दैट वी डू इन पुलिंग दिस मॉलिक्यूल्स टू सरफेस to form some surface, we actually should do some work against cohesion. Against cohesion. Okay, so we want to move this particular particle to here. We have to do some work against cohesion forces because this molecule is having very close bonding with its friends. You want to separate this with your friends. Okay, so we need some work. We have to do some energy. Okay, we have to spend some energy obviously. Now this work done in moving a particle from deep to the interface is requiring some energy, and that energy is actually stored in this molecule as surface energy. So basically the surface will be actually at some energy. Like for example, if you lift this pencil, for example, from this point to this point, to move this pencil from here to here, definitely I am doing work against gravity, yes or no? Otherwise if I leave, then definitely this pencil will fall. Okay, so in order to lift this, I am actually doing some work against gravity, and if I am doing against gravity, this work what I am doing will get stored as some form of energy in this body. What is that energy called? Any one of you? Let us suppose if I am lifting this from here to here, then definitely some energy is getting stored in this body. What is that energy called? Due to the elevation or due to potential, obviously. Okay, so potential energy. So likewise, in shifting this molecule here to here and forming certain new surface, we have something called the surface energy. Okay, and this surface energy is nothing but is actually equal to sigma into A, which is this A is the newly formed area because of doing this work. Work done is equal to surface energy, and this surface energy is mathematically equal to this A, which is newly formed area, because of doing this much amount of work. Okay, so sigma into A obviously. And you know, generally any body to reach equilibrium, it tries to attain minimum energy, okay, or minimum surface area, obviously, okay. In general, if this has to be minimum, then definitely sigma is, obviously, once you decide the fluids, sigma is fixed, then definitely this A has to come down. And for a given volume, the minimum surface area, mathematically, if you do first integration, first differentiation and equal to 0 and all, you will see, let us suppose if I make a cube, a sphere, a cuboid, for example, with same volumes, then definitely what happens? Out of these three, the minimum surface area will be for sphere, which also happens conceptually because of localized stretching at each and every point. Clear to all of you? ओके सर, जब हम मग को उल्टा क्ले वाटर में डिप करते हैं तो वो ऊपर आता है बायोंसी, ऑब्वियसली, ओके, क्योंकि प्लास्टिक मग का वेट बहुत कम होता है लेकिन पानी का बायोंसी बहुत ज्यादा होता है, ओके, सो दैट्स इट. Clear? And also one more thing that happens is, whenever you put mug, generally mug consists of air. Now whenever you start inserting it into the liquid will actually push the air. So the air which is already present in the mug will also try to push the mug in the upward direction. Okay? Clear to all of you? Now this is what you have. So this is newly formed area. So we have a lot of questions based on this. Like for example, they'll ask you these kind of some small questions. Let us suppose you have a droplet of size D. These are all some, you know, very nice simple questions. Now let us suppose if I split this droplet into n small droplets. Let us say they do like this. Let us suppose if I split this into n droplets, each of size radius small r, then what is the work done in splitting up these molecules? All these things they'll ask you. So it's very simple. So if you see, mass of the bigger sphere, it should be same as n into mass of this small particles, because mass cannot get, you know, disappeared. Okay, so whatever is the mass of this big droplet, same should be the mass of sum of all these droplets. Okay, so therefore if you see, density into pi, or because radius I have given you, fine, 4/3 pi r cube is equal to n into density into 4/3 pi r cube. Okay, so this is the mass actually. So obviously 4/3 pi, density gets cancelled because fluid is same in both the situations. N is equal to, or this r initially is equal to cube root of, okay, so r is equal to cube root of, or basically capital R divided by cube root of n in general. Okay, so this is how you get the radius, obviously, okay, because it's simple mass balance. Okay, now if you do simple mass balance, you will get this r is equal to capital R by cube root n. Now work done is equal to sigma at this interface. Okay, let us suppose if sigma, because of the fluid 1 and fluid 2, this is the interface, sigma into, then what is the total change in area? Area of that small droplets is n into 4 pi r square minus surface area of this is 4 pi r square. So this is the difference between these two, is the newly formed surface area, clearly. So sigma into 4 pi into, if you take r square out, for example, then we have n by r square minus 1, obviously. Okay, so what is this n by r square? You can clearly see this, small r square, right? So 4 pi r square, if you take common, n into r square by r square is what you have. Okay, so this is what you have. So small r by capital R in this case is 1 by cube root n. So square of this is sigma into 4 pi r square into n into this small r by r is 1 by cube root of n. So square of that, 1 by n power 2 by 3 minus 1. So this simplification will actually give you n power 1 by 3. So work done is equal to sigma 4 pi r square into n power 1 by 3 minus 1. Generally they give you this one n value as 2764, some cube value they'll give you, so that this calculation is actually simple for you. Okay, this kind of questions you might have done a lot of times. Okay, similarly they'll ask you this kind of question, like they'll give you some strip, and let us suppose if you have a piston like this, and let us suppose there is a fluid layer here. This is a fluid layer. Then they'll ask you to create surface of up to this particular point, what is the work done? Okay, now you have to do work against surface. Now in case of two free interfaces, let us suppose some cases what happened, like if you take a droplet, definitely inside also you have the same liquid, yes or no? Inside also you have the same liquid, obviously. here there is air. So obviously you have only one interface. The outer interface is only what you have. So this is the only interface that you have. So it has only one interface in case of droplets, liquid, jets, all these things. But when you take the bubble, what happens? If you, let us suppose if you blow a bubble, for example, then if you have a bubble, the liquid is only present along this bubble. Yes or no? The liquid film is present only along this bubble. Outside this bubble, you have air. Inside also you have air, obviously. Okay, so this is one interface between liquid and air, and inside you have one more interface. Understood? So that's how in case of bubbles and all we have two interfaces in general. Clear? And if you see clearly, let us suppose if this bubble or maybe droplet is bulging out. Okay, it's spherical, so obviously it is actually bulging out. If this is bulging out physically, definitely there should be some pressure difference between inside and outside. Yes or no? If this is Pi and this is Po, clearly there should be some pressure difference between in and outlet. Correct? Between inlet and also the outlet. Right? Now between inlet and outlet, if there is certain pressure difference, the bubble is actually bulging out. So can anyone tell me out of these two which is high, Pi or Po? Can anyone tell me out of these two which is high, Pi or Po, which is large actually out of this? Pi or Po? Pi is actually large, correct? So Pi is greater than Po. Now generally I just want to give you one equation which is called the Young-Laplace equation, which you generally see. Right now I'm not deriving it, okay, but I'm just giving you the equation. We'll derive all these things when we go for some full course. Now let us suppose if you have a fluid, let us suppose if you have some fluid body, for example, if you take certain interface, for example like this, at this point, let us suppose normally if you want to buy a watermelon, they'll cut a shape and they'll give you. Okay, so let us suppose if you have one such shape, then in that case, like for example, if you have this as the surface and let us suppose this is one radius of curvature, and maybe let us say this is another radius of curvature. Like when you cut a block, normally the radius will be equal only if it's sphere, but if it is not a sphere, the radius will not be equal. Okay, R1 is equal to R2 in case of sphere. Normally if you take some cylindrical or spherical object and if you cut, you can see R1 and R2 are same, but generally in regular bodies that need not be the case. So let us suppose if the inner pressure is Pi and the outer pressure acting is Po, this Pi minus Po is given as N times sigma at the interface into 1 by R1 plus 1 by R2 actually here. Okay, so this is what we have, and this N is basically number of active interfaces. Okay, so this is number of active interfaces. Clear? So this is number of active interfaces. Like for example, if you take a droplet, many of you might have mugged up this formula till now, that 2 sigma by R, 4 sigma by R, sigma by R, all this mugging up might have happened. But I'll tell you one thing here. Right now I'm not daring this because it takes again, this is not tough, but it's slightly time taking, that's it. Okay, so it takes around 25 to 20 minutes again, so that's right now I'm not doing. Okay, but if you have this equation, you see normally in case of droplet, if you have a droplet for example, okay, so if you have a droplet for example, if this is Pi, if this is Po, and let us suppose if this radius is R, and at this interface surface tension is sigma, Pi minus Po is equal to some constant into sigma by R. Can anyone tell me what is this constant? So small r by R is equal to 1 by n power 2 by 3. That too square हुआ, तो R by R is equal to n power 1 by 3 नहीं होगा. R by R is not 1 by n power 2 by 3. Okay, square is 1 n power 2 by 3. Like for example, if you see here in this, I have seen because of this square, I have written 2 by 3. Okay, this is actually 1 by 3. Okay. Understood, Manthan? N power 2 by 3 is actually square of that small r by capital R whole square. Okay. Now let us see. Can anyone tell me what is this constant? Come on, quick. Can anyone tell me what is the constant that comes here? Many of you might have doing this for so long, no? Like remembering these things. Hi, no one remembers what comes there. 2 sigma, 4 sigma, 8 sigma, whatever. Not remembered, right? I'll tell you. See here. In this equation, if you keep this, Pi minus Po is equal to N, number of active interfaces. If you have a droplet, how many active interfaces you have? Can anyone tell me? If you have a droplet, it's a drop. Okay, so in a droplet, how many active interfaces you have actually? Come on. How many active interfaces you have in case of a droplet? I didn't mug. Okay, good. If you don't mug up, it's really good. अरे ड्रॉपलेट में 2 इंटरफेस होगा क्या? एक ही होता है ना? Look, this is also fluid, no? Completely inside. This is also the same liquid. Inside there is no interface. Clear? सिर्फ एक ही इंटरफेस है बाहर में. There are no 2 interfaces. Okay? या 2 इंटरफेस नहीं है क्योंकि ड्रॉपलेट जो ड्रॉपलेट होता है ये सरफेस के अंदर भी पानी होता है ना. So दूसरा इंटरफेस कहाँ से आया? नहीं, सिर्फ एक ही इंटरफेस है. Okay? So there is one interface. 1 into sigma into. Now you take radii of curvature in 2 different directions. Okay, so let us suppose if this is one direction I'm going and if this is another direction I'm going, in both the directions radius of curvature is only r. So this is sigma into 2 by r. So this is 2 sigma by r, obviously. Okay, so sigma is equal to r. So this is 2 sigma by r actually. Now if you take a bubble, for example, if you take a bubble, then obviously you can see if this is interface Pi and Po, if this is a bubble, clearly you have one interface here inside, क्योंकि bubble जो होता है, so bubble के अंदर भी A होते हैं ना, so similarly on the outside also you have a second interface obviously. So in case of bubble you have 2 interfaces, so Pi minus Po is equal to 2 into sigma into 1 by r. Again bubble is also spherical, so this is 4 sigma by r obviously in case of bubble. Okay, that's it. Just if you know this formula, right now I'm not deriving because time is actually short, so right now I'm not deriving. Otherwise deriving this is also simple but actually a bit time taking. Some small trigonometry has to be done for the force balance. Okay, so in a detailed course or some other time I'll derive you the equation, but right now please listen to this. So this is 4 sigma by r. If you take a fluid jet, for example, if you take a fluid jet, let us suppose if there is a long fluid jet which is going, so obviously this cross section is circular and this fluid jet is of radius r, for example. Now clearly because of cylindrical shape there is Po and Pi inside, so if you take Pi minus Po in this case, now in fluid jet how many interfaces you have? What's the difference between a droplet and bubble? Number of surfaces. Okay, droplet is actually filled with fluid, liquid drop for example. Okay, so inside this sphere if you put your finger for example, still you get wet because there is fluid inside, but in case of bubble there is air or some other gas which is present. Okay, it's not another liquid again. Okay, now let us see in this case what are the number of interfaces that you have? Can anyone tell me what are the number of interfaces at this point? 1. Okay, there is only outer interface that is present. Inner again there is liquid, so 1 into sigma into. Now let us suppose you take 2 perpendicular radii of curvature, for example, let us suppose in this direction and also in this direction you take, so 1 by r plus 1 by, in the r2 direction that's a long stretch, 4 sigma by d hoga na sir, for this or this, for what? This is 4 sigma by d. Yes, this is 4 sigma by d because if you write radius as diameter by 2, 2 goes up and this is 4 sigma by d. Okay, I think the formulas are remembered in terms of diameters, so this is 8 sigma by d. Fine. Now let us talk about the case here. In this other direction it's a long jet, so obviously what is the radius of curvature? In this case if the jet is very long, then if you want to meet the ends, if you want to see the meeting of the ends, what should be the radius actually in this case? Let us suppose, look, I'll ask you this question in an easy manner. See, let us suppose you have a cycle. Now let us suppose if you are keeping radius increasing, then what happens? At some particular point you see this as a straight line, yes or no? The same case is here actually. So this is infinity. Okay, so this is infinity of radius curvature. Basically, it's a very large radius. So 1 by infinity. So clearly, this term is 0, and we have sigma by r, which is 2 sigma by d. That's it. Okay. So clear to all of you? This is 2 sigma by r, and of course that is 2 sigma by d actually in this case. Okay, so this is sigma by d, and this is 2 sigma by d, and all this is because of this particular Young Laplace equation. Right now we are not deriving due to time constraint, but it's a simple thing. Okay, so now this is the story of this. Now we will lastly see one sub consequence, which is capillarity. Consequence of surface tension. Now capillarity is basically the phenomena of raising or falling of fluid columns in narrow gaps. It can be due to cylinders, or it can be due to So can you summarize, please? Yeah, definitely, Tavan. Look, we have talked about surface tension. Okay, so we have seen whenever you come to this particular surface, the particles at the surface are in some imbalance between cohesion and adhesion forces, and this measure of cohesion and adhesion imbalance is basically this surface tension. Okay, because that effect of that imbalance decides the stretching capacity of the interface actually. Okay, so we have seen the units. Then we have seen something called surface energy and some physical concepts of surface tension, and then we have seen a bit of simple calculation, simple cases where this work done is calculated. Then this is the Young Laplace equation. Because of the bulging or particular shapes, inside and outside we have certain pressure difference. So for fluid jet, Pi minus P infinity is equal to 2 sigma by, look, only this is 0. Okay, this term is not 0. We have 1 by r. 1 by r plus 0 is 1 by r. That's it. Understood? So this is 1 by r plus this is 0, obviously. So 1 by r plus 0 gives you 1 by capital R. Okay, so 1 by capital R into sigma gives you sigma by r. Okay, so this is what we have. Now coming to this phenomena of rising or falling of the fluids in narrow gaps. Now why the fluid should actually rise or fall actually? Okay, so see here. For example, I'll just start with a simple example so that you can get it. Let us suppose if this is a small tube, and let us suppose here you have fluid, for example, like this. Okay, and let us suppose this is an opening clearly, and maybe this is also an opening. Yeah, the atmospheric pressure doesn't show much impact generally. Now let us suppose if there are certain conditions where this fluid got lifted up. Okay, this fluid got lifted up. When it gets lifted up, when it gets lifted down is very simple to understand. Look, if you take a water molecule here in general, they'll also be slightly, you can see this also happens slightly, this curvature will be there. Okay, of course it's in general not seen with naked eye, but you can feel this. Now if you take a particle here, for example, at this location inside the nanotube, why only in small tubes you see capillary? You see capillary is because whenever the tube is very small, whatever the substance that enters into the tube, that substance is surrounded by a lot of particles. Yes or no? Like for example, you can see, let us suppose if the tube is very narrow, if some particle enters here, this particle is subjected to adhesion forces by many of the surrounding molecules of the other substance. Yes or no? All these particles are very close to that particle and they all exert. But let us suppose if the tube is sufficiently large, then definitely what happens? Even though the particle comes there, this more than this cohesion and adhesion, so pressure forces, all these things comes into picture. Okay, so that's why this phenomena is generally seen only in very narrow channels. Now if you see in this case, I want to ask you one thing. Let us suppose on this particle, if cohesion forces is greater than adhesion forces, for example, if cohesion is greater than adhesion, please tell me, this particle will try to move along the tube or will it try to move along the fluid? If cohesion is strong, this particle which is here will try to move along the tube, or will it try to move towards the fluid? Tell me, type tube or fluid in the options. In this particle, cohesion is actually large. In this region, cohesion is actually large. If cohesion is sufficiently large, then will it move tube or fluid? Type in the chat box. Towards fluid, obviously. Okay, so towards fluid. If this is moving towards fluid, then compared to this free surface, this fluid molecules will end up somewhere here. Yes or no? Correct? Actually, in atmospheric condition, if you put the tube, the water should actually go up to the mark, but because of the imbalance between cohesion and adhesion, if cohesions are strong, definitely this molecule will try to come down, and if adhesion is strong, this particle will actually tend to move along the tube direction. Yes or no? So that means, in general, if you have cohesion more than adhesion, we see capillary depression. Depression is basically a drop in the level. Okay, we see capillary depression. And similarly, if cohesion is less than adhesion, or basically you can say adhesion, okay, cohesion is less than adhesion, you can say adhesion, we see a phenomena called capillary rise. Actually, we see a phenomena called capillary rise, obviously here. Clear? Adhesion is between force due to different molecules. Like for example, you see Fevicol and wood. If you stick, they stick to each other. Okay, so because Fevicol is an adhesive, you cannot stick Fevicol with Fevicol again. Okay, so Fevicol with some other substance. So the bonding is adhesive bond in that case. Clear? Adhesion forces means basically the force of attraction between dissimilar molecules. Okay, so it's very simple. If this is the molecule here, if the pulling forces, means the cohesion forces, are very high drastically, then definitely this particle will try to move in the downward direction. Or if this particle is experienced to high adhesion forces due to this glass tube or this glass material, it tries to move up. That's what we have, a capillary rise and a capillary fall in general. Is this clear to all of you? Now, if you want to quantify, so that's why generally in narrow channels, in very small gaps, you see the fluid is actually either moving up or coming down in general. Okay, we suck cool drinks or juices from pipe. Here also adhesion happens. Adhesion will be there slightly, but more than adhesion, your pressure difference. Normally for sucking the fluid or for drinking the fluid, you will actually apply certain pressure difference. So that's why the fluid actually comes up. It's like a flow through pipe, for example. Okay, but it's not due to the lifting is not due to the adhesion forces in that case. Okay, it's because of your pressure difference that you create for sucking the fluid. Okay, now anyway, let us see. Now if I want to calculate mathematically what is this H actually? Okay, to this meniscus I have taken H, for example. We have some important definition which is called the contact angle. Like for example, if you take a surface, if you have a droplet, for example, like this, let us suppose if you have a droplet, then you can clearly see with this surface, this is making a contact at an angle which is equal to this, correct? So this is called the contact angle theta in general. Okay, so this is the contact angle theta. Now try to understand one thing. Or let us suppose if this is the contact angle. Similarly here, this fluid will try to make contact at this angle. Yes or no? So this is the contact angle in this case. So the adhesion is acting along this. That's why the fluid is actually bending towards that. Obviously, force is equal to mass into acceleration. All the displacements, all the velocities will happen in the direction of application of force, obviously. Okay, so that's why whenever this fluid is getting displaced in this particular pattern, that means the adhesion or the surface tension, basically the net effect between adhesion and cohesion, which is nothing but the surface tension. This surface tension is acting at this particular angle actually. Okay, did you all understand this concept of contact angle? Normally, let us suppose it's very simple. If you take a block and if you apply force in this direction, the displacement of all the, let us suppose if you take a block like this, if you apply the displacement, if you apply the force on this face like this, all the particles at this interface, they move in the direction of application of force, correct? obviously. So similarly here, if the fluid is actually taking this shape, that means the net effective force acting on the fluid particles is basically in that direction. Obviously, if this is the direction, then definitely fluid particles will make contact in that particular sense, and this angle is actually theta, okay, because this is the angle with respect to this tube along which it is making contact. So that's theta, obviously. Okay, now this is theta. Then clearly you can understand, if you take the pipe, for this fluid to stay like this, the weight of this particular part of the fluid should be balanced by the surface tension all over the 360 degrees of the circumference. There is surface tension. So the weight of this fluid block has to be supported by this surface tension forces. Yes or no? So obviously, if you see, surface tension is acting per unit length. So what is the total length along which it is acting? Nothing but all over the circumference there is a fluid solid contact. So fluid mechanics is difficult? No, not at all. Okay, so see here, this is sigma cos theta. So if this is sigma cos theta, if you multiply with length, okay, so what is the solid fluid contact length actually at the interface? Can anyone tell me? At that particular interface, let us suppose if you have an interface, at that interface the fluid and solid are getting into touch along the circumference of the tube. Yes or no? Yes. So that's getting along the that's getting into contact along the circumference of the tube, obviously. So the surface tension will be all over at the interface. So sigma into sigma cos theta into pi d, or 2 pi r, or basically pi into diameter. Okay, so 2 pi r, or basically if you call this as diameter d, for example, then you have pi d. This is the surface tension force which is trying to lift the fluid. Obviously this should be balanced by the weight of the fluid. So what is weight of the fluid? Density into, let us suppose if you neglect the small meniscus effects, this is pi by 4 d square into h. This is the volume of the fluid in this small channel, because pi by 4 d square is cross section multiplied by height into g, obviously. So this is what you have. So if you simplify this, then definitely you can see pi and pi gets cancelled, d will cancel this one time. So we have h is equal to this 4, if it comes to the right hand side, 4 sigma cos theta by rho g d is what we have as the expression finally. Okay, single equation, only one equation, that's it. Pi r square. Yeah, 2 pi r is the circumferential contact, so this is the single equation. Okay, so this is how you have. Similarly, in case of capillary depression, the depression, the equivalent mass, the imaginary mass of the fluid which is here should be equal to the surface tension force. So in capillary depression, you can clearly see that like h is again equal to minus 4 sigma cos theta by rho gd. So this minus sign will actually decide the, because weight and surface tension both will act. So this imaginary mass of the fluid which is here, if you make a balance, you will get the same expression but with a minus sign. Here I want to tell you one thing. There are two fluids which are called wetting and non-wetting fluids, because just quickly we'll go wetting and non-wetting fluids actually. Okay, so what are these wetting and non-wetting fluids? Let us suppose if you keep a droplet here, for example, let us suppose you keep a droplet here, and slowly this droplet is spreading over the surface, for example. Okay, so let us suppose if that's the droplet, then eventually with the time, let us suppose if this is happening. Okay, if this is happening, means the droplet is actually getting spread on the surface, it is wetting actually. Okay, so if the surface has to wet, then definitely you can try to understand. Let us suppose initially if you have this molecule, for wetting to happen, this molecule which is here should actually land up here. Yes or no? If it want to wet. Yes, whole area will also excite, but compared to density of the liquid and all, the density of air is very less. That's why we are neglecting the weight of the air acting on the liquid column. That's it. Okay, Ladani? Come on. Try to understand this. If this has to wet this, means if this droplet has to spread on this surface. So I am able to understand all the concepts, but still I am not getting confidence in subject. Just keep solving questions, you will get confidence. Okay. So see here. If this particle has to land here, what should happen physically? This molecule on the droplet is exerted due to certain cohesion forces. Okay. Similarly, this molecule will also get attracted because of this molecule on the surface due to adhesion. Yes or no? Because all the molecules of this surface will also try to attract this molecule. Similarly, this molecule will also be attracted by molecules on the bubble actually, or in the droplet actually. Okay. Now, when these two forces are acting, but finally the droplet is deciding to come from this location to this location, that means in this case, out of this cohesion and adhesion, which is stronger in case of spreading, let us suppose if this droplet is spreading uniformly, then for this droplet, instead of having cohesion and adhesion both, but still at the end the droplet is trying to come and settle here, that means out of cohesion and adhesion, which is strong actually, which is strong, out of cohesion forces and adhesion forces, which is strong. Everyone should type in the chat box. Obviously, adhesion forces. Okay. So, in case of wetting fluids, adhesion is actually greater than cohesion, and this case is opposite. Adhesion. Like for examples, you see in general, mercury, and this is water, for example, in this case. In this case, if you see carefully, out of these two, let us suppose if some mercury gets spilled in the floor, you can actually collect it. Like how you can collect a solid, similarly you can collect the downpoured mercury in a bottle and you can move. But water you cannot do that, okay? Because obviously water gets spreaded over the surface. Clear? Now you can see the contact angle in this case, because whenever adhesion is greater than cohesion, the contact will be made at an angle theta less than 90. Like in this case, whenever adhesion is greater than cohesion, you can see whenever adhesion is actually greater than cohesion, you have the capillary rise, theta is actually positive and all in this case. So similarly, this is the case, and here it is greater than 90. Normally for mercury and water or glass interface, this is like 128 degrees approximately. Okay. And here for water, I mean pure water, this is pure water and clean glass. This is also clean glass, obviously. So pure water and clean glass, you will see generally this theta is 0 in this case. Okay. The water will flatly spread on the glass actually. Okay, you can see. Okay. So these are different things that we have. So weight also work. Where in the previous case? Yeah, because weight will try to pull gravity will always try to pull the liquid down, no? But that's not coming down, it's in equilibrium because of the surface tension force. Like for example, you can see, I would like to give 1-2 more examples here. Let us suppose you have a cylinder of diameter d, and let us suppose inside you have one more cylinder of diameter small d. Okay, this is small d. Now let us suppose you have the fluid up to this level, and inside the annulus, let us suppose you have certain ways of fluid. Okay, annulus is the gap between these two, and obviously in this tube also you have certain ways of the fluid. Okay, then if you say this is H1, if you say this as H1, and if you see up to this as H2, definitely you can see H1 is directly 4 sigma cos theta by rho GD, directly just capillarize inside a tube. But in the annulus, how you do? Look, sigma cos theta into, now whenever you keep the tube inside at the annulus, the fluid and solid will get contact at 2 locations. One location is around the circumference of inner cylinder, and one is along the circumference of the outer cylinder, correct? Let us suppose if you dip a glass tube into one more glass tube, the fluid will actually make a contact with the inner tube, and also it makes a contact with the outer tube, obviously. Okay, so pi d plus pi d is equal to, now the weight of the fluid, which is balancing, is obviously density of the fluid, into pi by 4 d square minus d square into g into H2, obviously. Okay, this is the weight of the fluid, obviously, because area of cross section of the fluid in the annulus is nothing but pi by 4 d square minus d square. So if you do certain simplifications, you can see pi gets cancelled in all the terms, then this d plus d will cancel this as d minus d, obviously. So H2 is equal to 4 sigma cos theta by rho g d minus d, obviously. That's it. Okay, so this is what we have. Clear? And if there is no inner pipe, clearly, you know, 4 sigma cos theta by rho g capital D is the capital device. That's what. Like, what might be the situation? Just you have to apply surface tension force should actually balance the weight. That's it. Okay, so clear to all of you? Can you explain pi d plus pi d? Yeah, because whenever you see the top view, for example, for the fluid which is in this location, the fluid will make contact along this and also along this inner, correct? Along the outer surface of the inner tube and also the inner surface of the outer tube, the fluid makes contact. So there are two interfaces where you have fluid solid contact. Okay, so obviously surface tension will be at these two interfaces. Clear? Now let us see. Acha, today you want me to teach fast. Yesterday you asked me to teach slow. Okay, good. So see here. One last thing that we generally go here is, before this start this pressure, non-Newtonian fluids. This is slightly important sometimes. So see here. Normally we see tau is equal to mu into shear strain weight. If this is xy, this is also in place xy. This is Newton's law of viscosity. And we have also seen this, sometimes this is equal to mu into du by dy in general. Okay, and this is the fluids which obey Newton's law are called Newtonian fluids, obviously. Means if you change this gamma dot xy, this tau xy gets similarly changed, but this mu will actually stay same. Okay, so mu will actually go same. But now if you see, in general, this need not be the equation for all the cases. The actual equation for any fluid in general is actually given by T is equal to tau naught plus A into du by dy whole power n, obviously. Okay, so this is the equation, and this tau naught is called yield shear strength. Yield shear stress. A is flow consistency index, obviously. And n is flow behavior index. Okay. Now, why these are called behavior? Why n is called the flow behavior index and all? We will see just now. Within 2 minutes. This tau naught is basically, look, I have told you one thing in the beginning of the fluid mechanics, that any substance which which deforms continuously under action of even infinitesimally small shear stress is what I have told you, correct? That has little slight exemption. Normally you have one class of fluids which is called viscoelastic fluids. Viscoelastic fluids. Okay, so what is this viscoelastic fluids is, immediately as soon as you start applying slight amount of shear stress, the fluid will not start deforming. Like for example, your toothpaste. Okay, let us suppose in the morning when you are pressing the toothpaste, it's not like you apply very small, infinitesimally small shear stress and toothpaste will immediately start flowing. It won't flow. Okay, so you have to apply certain enough amount of shear stress on that. Okay, so like that, to start motion or to start deformation or to start the flow of some fluids, the shear stress that you apply is not really infinitesimal. There is certain finite amount of shear stress to start the flow. Okay, so that's actually called the yield shear stress. Like example, your toothpaste. Okay, or Kisan jam, many of you might have seen. Normally if you have a jam and all, if you just press it, it won't immediately start flowing. It needs some time. Okay, I mean it needs certain shear stress. Now in this case, if you see, for tau naught is equal to 0, A is equal to mu, n is equal to 1. This model, which is actually called Ostwald-Diwali's model, D-Wallis model actually. Okay, so this is Ostwald-Diwali's model. Now this Ostwald-Diwali's model gets reduced to, because you can see clearly, mu into du by dy. This gets into Newton's model, obviously under these conditions. Newton's model actually. Okay, some of topics is getting shuffled. No, why? We talked of properties of fluids, then we are talking about non-Newtonian fluids. That's it. Okay, so see here, this is tau is equal to mu into du by dy, which is like the Newton's model. Now clearly you can understand one thing. If tau naught is equal to 0 for majority of the fluids, like we take in general, because generally water, air or kerosene, gasoline, all these fluids, they generally have tau naught is equal to 0 obviously. Okay. Now some I cannot see your previous comments, Motor World. Okay, so maybe, so if tau naught is equal to 0, so this is in general, you can see tau is equal to a into du by dy whole power n. This expression can be slightly modified as a into du by dy whole power n minus 1 into du by dy actually. Now this combination which is here, if you call this as, for example, eta, this expression can be written as, in terms of Newton's closed law, this can be written as du by dy actually, and this eta is actually called apparent viscosity. Apparent viscosity, and these two constants a and n depends upon the type of fluid what we are taking, and we'll have that. So can you share your FM notes? I studied in Hinglish batch. Okay, maybe we can find it on Telegram groups or somewhere. Okay, and as I told you, my Telegram group is like this is t.me/pw. Very nice, sir. Okay, so this is the group actually. Okay, if some of you want to wish to join, you can actually join this. Okay, fine. Okay, so now what about this apparent viscosity is? Look, I'll ask you some questions. Tau du by dy actually here, and you know one thing, Newtonian fluid is like this. Clearly it has some fixed slope, so this is Newtonian fluid, constant Newtonian. Okay, where n is equal to 1 obviously. Okay, and tau naught is equal to 0. Tau naught is equal to 0 obviously. Here you can see tau naught is equal to 0, so n is equal to 1. Let us say n is equal to 1, because n is equal to 1 gives you Newtonian fluid. Now you can see one thing. Let us suppose if I have a fluid where if du by dy increases, the viscosity also increases, for example. Okay, there will be some fluids where you can actually see whenever you try to increase the shear rate, the force you have to apply is very fast actually. Like for example, look, if I want to deform the fluid slowly, okay, if I want to deform the fluid slowly, it is easy for me, but let us suppose if I want to deform it fast, I'll feel it very difficult. Like for example, wet sand. Okay, let us suppose if you go to beach sometime to play, if you go to beach, what happens? Let us suppose if there is some wet sand. If there is wet sand, then if you slowly try to disturb the wet sand, for example, okay, so suspension of sand in water, wet sand is basically suspension of this sand particles in water. So if you slightly try to deform the sand, it is easy for you, you can actually easily deform that. But let us suppose if you try to put it hard, means like for example if you try to push it very hard, then definitely what happens, you will feel very high resistance for the hand. Yes or no? Correct? Have you ever observed this? Like in case of suspension of sand, then definitely what happens, if you try to deform it faster, the shear stress or the resistance offered that you feel for your hand will be large. Correct? In such cases, one thing that is, if du by dy is increasing, means if du is fast, means if the velocity at which you are trying to disturb is actually very fast, then this term, the resistance for the movement of the particles, will also be very large in that case. Okay, so there could be some fluids where definitely if du by dy is increasing, then definitely eta will also increase. Now if eta is increasing, can anyone tell me, if this is increasing, then this quantity is also increasing, that means this power has to be positive or negative? My question is, if du by dy is increasing, then if this term has to increase, this power n minus 1 should be positive or negative? N minus 1 should be positive or negative? It should be positive. If n minus 1 is positive, this implies n should be greater than 1 obviously. Correct? N should be greater than 1, and in this case you can see, if this is tau, like tau is equal to eta into du by dy. So eta is nothing but slope of the tangent to this tau versus du by dy. In this case, eta greater than 1, the slope should actually keeps increasing with du by dy. If du by dy is increasing, when n is greater than 1, this slope also increases. Means the curve should be in this particular fashion. Okay, because if you take tangent at low values of du by dy, the tangent slope is also small. Like for example, if that slope is apparent viscosity, because tau is equal to eta into du by dy, at higher weights, as you increase your du by dy, the slope of the tangent will keep on increasing. Yes or no? And that's how, if you have a curve with increasing slope, that particular fluids are called shear thickening fluids. Shear thickening fluids. And in this case, your n is actually greater than 1, and obviously that actually gives you, like, they're also called as dilatant. Okay, in the olden days, the terminology that was used is called dilatant. Actually, curve should be upwards for n greater than 1. Yes, for n greater than 1, curve should be actually upwards. In that case, they are called shear thickening, because as you keep on applying shear faster and faster, they become thick and more thick, because the resistance, normally you see thickness is generally defined with stickiness actually. So if it becomes thick, that means it is not easy for you to deform actually. Okay, so that's what the fluids will actually get thickened, and obviously they are called the shear thickening fluids. Okay, and clearly you can see the other class when slope decreases, obviously n less than 1 in this case. So they are called shear thinning fluids. Or do anyone know what is the other name for these fluids? Shear thinning, or what is it called? They are called generally pseudoplastics. Okay, so pseudoplastic fluids. Pseudoplastics. Okay, so clearly you can see, if you take tangents at different locations, as you increase du by dy, the slope of the tangents keep decreasing, because the tangent becomes flat as you increase your du by dy. Understood? Now similarly, we have some fluids where initially for up to certain shear stress there won't be any deformation. So if you start applying shear stress till some amount of shear stress, there won't be any U that you can see. You cannot see any deformation happening, and at this point they start, this is called the yield shear stress. Okay, and for all these three classes, tau naught is actually 0, and in this case the fluid will be having 0 deformation till this point, and then it moves. Like these are called Bingham plastics. Or these are special class of, again, viscoelastic fluids, so they are called Bingham plastics. Now in general, can anyone tell me what does this line represent? Which type of fluid does this line represent? Can anyone tell me? What will be the behavior of shear thinning fluids? Like for example, curd. Okay, curd. You can check curd. In case of curd, what happens? As you churn faster, it is easy to churn again and again. Yes or no? Initially churning will be difficult, but later what happens? Once you started churning, the fluid at higher deformation rates will actually keep, will get into very diluted, and obviously we feel very easy to move the churner. Okay, so that's what. Clear? Now you can see this is ideal fluid, obviously. Yes, this is the line for ideal fluid. Why it's called ideal fluid? Because as much as you deform, there is no shear stress. Shear stress will come into picture only when there is viscosity, but because if the fluid is not experiencing any shear stress with respect to velocity gradients, that means the fluid internally is not offering any resistance. Obviously it's a ideal fluid. Okay, because if there is no tau, that means practically the fluid by its motion is not at all offering any resistance, means practically the fluid don't have any viscosity. Okay, so mu is 0, and clearly this vertical line, can anyone tell me what is this vertical line? This vertical line, can anyone tell me what is that vertical line actually? Solid, obviously. Okay, so this is a ideal solid, rigid body, perfectly rigid. Okay, so these are ideal solids, obviously. Okay, because as much as you apply shear stress, whatever you do, you cannot displace the particles. Okay, so solid, basically it's a practically high solid actually. Clear to all of you? Did you all understand? Till now, some of you at least might be mugging up these graphs actually. Okay, you draw a straight line, then one which is above is pseudoplastic, one which is below is what is this? Shear thickening means dilatant, or sometimes in some books they keep this. Okay, you know, this is Newtonian, this is dilatant, this is pseudoplastic is what they'll keep. Some books you might have also seen these diagrams like this. Okay, it's not like pseudoplastic is above the straight line, dilatant is below the straight line. No, this is not the logic. Okay, whenever you see slope is increasing, they are shear thickening, and whenever they are slope decreasing, they are shear thinning. Okay, like this is the idea behind all this, and this Oswald-Wallis model is actually the case. In tomorrow's class I'll do one thing. In the notes I'll put a slide, because I have a slide actually which I have kept in yesterday's class, but yesterday unfortunately time is not sufficient. So in yesterday's class we have kept a slide regarding each type of fluid. Okay, so like for example dilatant, you see this sand suspension in water and all these things. Okay, now you can see there is one more thing which is called the time dependent. These all are gradient dependent. This set of fluids is velocity gradient dependent. Similarly we have something called time dependent fluids. Some fluids, what they do, with respect to time they get thickened. Like for example you can see nail polish, for example. Okay, if you see a nail polish, the new nail polish will be generally in liquid form. Now if you keep that nail polish for a few months without using it, whenever you open that you will see the liquid particles get very thickened almost. Okay, so the viscosity will actually increase very much. Like almost if you keep a nail polish for some days, some months without using it, when you again open it after a few months, you feel like it's almost like a gel, a solidified gel. Yes or no? Have you ever seen this in your home? Normally, you know, when our mother or sister generally when they are putting the nail polish, yes, you can see normally if you don't use that nail polish for a few months in general, then when you take it out, then definitely it gets into very, you know, sticky substances. It gets converted as solid gel. So basically with respect to time, some fluids actually gain viscosity, so they are called time thickening. Time thickening. Like for example you can see if this is a time and if this is apparent viscosity, then clearly you can see they actually increase slope with time. And obviously the second class will be time thinning. Time thinning, with respect to time these guys actually decrease the slope, so these are called time thickening and time thinning. Time thickening and time thinning fluids. Time thinning. Can anyone know what is the other name for this? Yeah, so can anyone tell me what is the other name for this time thickening fluids? What is the other name for this time thickening fluids? Because you know, people who all mugged up this, they are not seeing two types of names in this. Yes, it is basically thixotropic. Okay, so thixotropic and heliophectic, right? So this is basically thixotropic and this is actually heliophectic, correct? So time thickening are called thixotropic and this is basically the heliophectic fluids. Okay, so this is what we have about the non-Newtonian fluids in this class actually, because sometimes they ask you, they'll give you some graph and they'll ask you n greater than 1, n less than 1, all these things they'll ask you. So basically for these three things, tau naught is 0 in all these cases, n greater than 1, tau naught is equal to 0, n is equal to 1, tau naught is equal to 0, n greater than 1, sorry, n less than 1 in that case, tau naught is not equal to 0 and n is equal to 1 if it's a straight line. If n is greater than 1, again this curve and the upper curve will actually come. Okay, so this is the understanding of equation of time dependent fluid. Actually we don't have the equation in general in this particular, normally in any textbooks I have not seen till now, but definitely if you go through some research papers you can get that equation. Okay. Okay, blood falls into which type of dependent? This dilatant, because blood generally gets thickened velocity gradients. Okay, we'll see how. We'll post certain slide which gives a lot of examples actually about this. Okay, so that's what we have in properties of fluids. Now coming to this concept of pressure, actually I was supposed to start at this point today, but you know, some detailed discussion on fluid properties are important, because from pressure and its measurements the things go mathematical. Okay, but in understanding the first chapter is really crucial. Okay, because properties of fluids is
A really important thing which we keep on using again and again and again throughout this course. Okay, clear? So pressure is a very small concept. Maybe today I'll give certain introduction to pressure within next only 5 minutes is left. Fine, I'll give you certain introduction to pressure. We will then see pressure questions on hydrostatics, manometers and all in tomorrow's session. Okay, is that okay to all of you? Because did you all understand fluid and its properties in a nice way? Definitely. Did all of your concepts, all of your doubts in the mind, all of them got cleared? Okay. Definitely, you all might have got certain new points in fluid mechanics, definitely, at some locations, at some points of explanations. Okay, so I hope you all understood that in a good way, because got a clear picture. Fine. So that should obviously be there. Okay, so first chapter is really important. Okay, from second it's mathematical. We can go quickly. Equations, like you will see the yesterday's Vande Bharat when I saw again. Okay, when I start fluid statics and all, again you can see a lot of mathematical equations are there. So we will then again tomorrow don't say that you please slow down again. Okay, because yesterday you told me to slow down, today you are telling me to speed up. So tomorrow not slow down again. Okay, so get ready for the equations of maths and all. Clear? Now this pressure and its measurement, let us see a bit of simple idea. So obviously looking at the formulas, pressure and stress both will have the same under formula obviously, but in case of stress and pressure, stress is internal effect which gets generated between the equation, and pressure is due to the external effect of fluid on any body. Okay, so you can see pressure is normally due to external effect, stress is due to internal resistance. Intensity of this internal resistance is generally called stress, and intensity of external effect is called this. Okay, so pressure, if you see clearly, pressure we have something like, okay, so pressure we have something like the intensity of external normal compressive load or compressive force, you can say compressive force. Like for example, if you take a small area dA at this point, so let us suppose if you take a small area dA, then obviously at this point this happens certain pressure which is acting, and this pressure is written as limit dA, or let us say delta A for example. So limit delta A tends to 0, delta F by delta A in general. Okay, so this delta A is very small in general. So pressure normally at a point we talk in actual practice, because if area gets smaller and smaller and smaller, finally we reach a point actually. So this is P, and obviously this P is actually measure of delta F which is acting on this small area. Okay, and the intensity of that force will be delta F by delta A obviously. Okay, so your teaching pattern is fast, but I watched yesterday's video again and today's topics getting is more clear. Yeah, definitely. Okay, you have to do little extra work obviously. Okay, कल एक्चुअली मेरे को एक कमेंट बहुत फनी लगा. वीडियो के बाद मैंने कमेंट्स चेक किया, उस टाइम पे एक बंदे ने कमेंट किया कि सर लगता है कि आपने 2x में पढ़ा है. ओके, वीडियो में 2x में पढ़ा है. देन उसके नीचे एक और एक कमेंट भी है, तो बेटा 0.5 स्पीड में पढ़ लो आप, मतलब वीडियो का स्पीड 0.5 बना के तब पढ़ लो, सो आसान हो जाएगा. ओके, सो दिस टाइप ऑफ कमेंट्स आर रियली सम फन. So P is equal to this. Okay, so if you take the units again, SI, Newton, force, area, meter square. Okay, you generally call it pascals. Okay, so pascals obviously. In we have a lot of conversions again for 1 atmosphere and all. When I'm teaching you barometers, I'll again teach all those things because I'll roughly give you the idea today, because I think the time is almost done. Look, I'll give you some basic idea how we are going to proceed in tomorrow's class. Basically in tomorrow's class we'll see, normally if you take pressure actually, so from this pressure we will see the units of pressure. Okay, measurement of pressure actually. In measurement of pressure we will see what is the first construction, that is nothing but piezometer. In piezometer, how to measure the pressure, what is the concept that we go in general, and before piezometer even we'll see certain hydrostatic law, Pascal's law, all these things. We'll apply certain equations, some bit of mathematical stuff we do again. So after that, when we see piezometers has got some defects. To overcome the defects in piezometers, we have got U-tube manometers. Okay, then to make the measurement in U-tube manometers better, we got inclined tube manometers. Why? We will connect each point. Why these U-tube manometers are not very highly accurate as compared to inclined tube manometers? Okay, so we will see. Then instead of inclined tube, why we go for some other differential tube manometers? And instead of differential tube manometers, why we go for inverted tube manometers? Okay, so these are the classes we have: piezometer, U-tube manometer, inclined tube manometer, differential manometer, and inverted tube manometer. So these are the things that we have here. So we will see the connection from each step. We will start with the building blocks and we will keep on moving forward. Okay, so that's how we actually move forward, and that's how we'll solve some questions of this manometers and all. Clear? Barometers, manometers, we'll do a lot of things on this. Okay, and so if any doubt occur, how can we ask? As I told you, you can always approach me at this group t.me/pw Vinay sir. Okay, so basically if you want to generally today, if I want to summarize, I have put some questions also, but today we unfortunately didn't find time. So we started about Newtonian with a non-fluids. We have also seen the properties like bulk modulus, then Mach number. Okay, Mach number is of course not a property, that it's a ratio basically. So we have also seen the surface tension property. We have seen all the consequences of surface tension. Did you all understand all these things? Let us suppose if I give you a quick review, like for example, you can see we have started with recap slightly, then we have solved this beautiful question. Someone is asking me to show how the viscous forces are coming actually here. Okay, so viscous force is because normally the viscous force is all around this edge, yes or no? At every edge, means if you take the cylinder all over the 360 degrees, when this cylinder is actually falling in this channel, actually this is the cut cross section actually. Okay, but you can clearly see they are told a cylinder of weight slides down from west in a vertical cube whose inner surface. Okay, so whenever there is a cube, obviously there is some viscous effects at all the 360 degrees. So obviously this actually comes down in the viscous layer. Okay, so whenever this is coming in viscous layer, viscous forces is equal to shear stress into area of contact. Okay, so shear stress is mu into velocity gradient. So if you see in this small gap, if you expand this, every particle here is on west and every particle here is moving at a velocity v along with this cylinder. Okay, so if you see a velocity profile, then clearly you can understand that there exists a velocity gradient in this gap h. So if this is the situation, velocity gradient is in a gap of h, velocity is increasing from 0 to v, so v by h is the velocity gradient. That's it. Okay, that's how we calculate the viscous force. Clear? Because someone was asking it out. So then after we have solved this differential equation simple, we have seen the concepts of bulk modulus, then incompressible and fluid and flows, surface tension, consequences. Then after Young Laplace equation, then we have solved certain wetting and non-wetting phenomena. Then this non-Newtonian fluids also. We have seen the concept of pressure. Hydrostatic forces and pressure we will see generally tomorrow. Okay, so I thought of solving some questions, but anyway the time is up, so we will stop here for today. So this is the brief summary of what you have. So please upload your FM full notes. Acha, that I think I have to take permission and will let you know. Okay, पेड बैचेस में रिवीजन करा जाएगा ना? हाँ पक्का जाएगा. Even I think we have started also for the people who joined in 1.0 batches. For them the syllabus was done, so we have started revision batches as well. Okay, so if you want to approach me at any time, you can actually definitely talk to me at this location. This is my Telegram channel ID, so you can follow it over here. Okay, so fine, that's it. Okay, please tell us how to practice a question in fluid mechanics for gate. Generally, if you solve PYQs and also this Super 1500, all these batches will definitely put some good practice. After that, like if you solve unsolved questions of Rankine-White, it would be beneficial. Okay, आज हमने थोड़ा सा ब्रेक्स लगाया इस गाड़ी में, लेकिन कल मैं थोड़ा सा एक्सेलेरेटर भी दबाता हूँ. Okay, fine. So thank you all. I hope you all enjoyed and liked this session. So we'll meet again tomorrow at 7 AM. We will continue with pressure and hydrostatics. Okay. Oh, thanks Arjun, Nitish. Yeah, fine. Okay. You have great content. Acha, fine. Yeah, thank you. Fine. every chapter, it's not like this is the first chapter, so I'm doing at this detail. Every chapter will move at the same pace, at same detail, so that at this course will definitely, I'll make sure that this course will be maximum benefit to you, and you'll get out of it in the examination, and also for the knowledge regarding interviews and all. Okay. But right now I cannot show all the derivations and all how things comes, because obviously time is a constraint. So just it's a fast track. Okay. So thank you all. We'll meet tomorrow at 7 AM and we will discuss on this pressure and its measurements and hydrostatics. Okay. So thank you all. Taking care. Signing off. Bye.